for another 2 months. So thanks, John, for this introduction to the Institute, and welcome to all of you for our summer school. And I would just like to say 1 or 2 words about some technical details. So we have poster sessions, I think tomorrow and the next Tuesday, but they are sort of rather short together with the wine reception, but you can hang your posters whenever you want. So you can hang them today in the little room left of the lecture hall, and they can hang over the 2 weeks, and you can track wherever you want to your poster over the 2 weeks to explain it, right? So the poster sessions are just that we can be sure people are at their posters at that time, but you're free to use it all the time. And then you will see on the screens outside there is an additional session popping up Wednesday afternoon, informal get-together, so just ignore that, right? We need to remove that. So Wednesday afternoon is really free. So in order to, let's say, not overload you, and then you will stay till the end and listen to the lecture. So saying something about the lectures, if you look through the program, you will see it's a very wide range of subjects, right? So it goes from, let's say, rather biophysical to rather mathematical. And so I guess everyone will be taken out of their comfort zone at some point. So just please don't give up. If something is complicated, I guess this will even happen to the lecturers if they sit with the other lecturers. And with this, I hand over to Edgar, who is our first speaker, Edgar Knobloch from the University of California, and he will speak about localized structures and in particular in fluid flows. And I will act as, let's say, a loose chairman for today, and will ask others to do so.
Okay, so good morning, everyone, and thank you, Uwe, for the introduction. So I don't know why I was selected to be the first one, but I hope the organizers will not live to regret their decision. But my purpose in these 2 lectures is to say something about spatial localization in general, and in particular with applications to fluid flows. So the first lecture will be So in the first lecture, I'm going to talk about a very simple example called the Swift-Homburg equation, which exhibits localized structures. And I want to explain why it does so and some of the properties of those localized structures. Then I'm going to talk about a slightly less simple example, and that's the same equations but in 2 spatial dimensions. So I'm going to talk about localization in two directions. And then I have a bunch of other topics. I'm going to talk about the Swift-Homburg, the conserved Swift-Homburg equation, which is a model for mesoscopic solidification processes, for example. And I'll talk about the propagation of solidification fronts into a quenched liquid, for example. So that's front motion into an unstable state, so-called pulled fronts. I'm also going to talk about fronts propagating to a stable state, so-called pushed fronts, and the mathematics there is quite different, and the behavior is quite different also. And then in the last part of the second lecture, I'm going to show you how some of the same phenomena that we've seen in these simple equations actually appear in real physical systems described by Navier-Stokes. So that's briefly the program. I'm going to make this quite general because, as Uwe said, the audience is very broad. But let me begin by mentioning that my first ever talk on localized states was in this room. In August 2005, we had a program on pattern formation in large domains, and I had just, in fact, found some very interesting localized structures, and I was explaining people about what we had found, and that this is really an interesting topic to think about. And I think since then, this whole subject has exploded tremendously, and I'm going to try to explain what some of the developments that have happened since 2005 have been. So what was it that I talked about 8 years ago? Well, I showed these results. These come from binary fluid convection. So that's a convection in a mixture, a miscible mixture of two components. You can think of water and ethanol. That's my favorite mixture. But other people think about, helium-3, helium-4, and other less palatable things. And what you see here is a two-dimensional layer. It's heated uniformly from below, right? So you're putting energy into the system everywhere at the same rate. The hotter boundary is at the bottom. The colder boundary is at the top. And what you see in the top panel are the stream function of the solution, and it's colored according to whether the hot fluid is rising, that's red, cold fluid descending, that's blue. And so you see that there is a roll like this, usual convection roll. But the remarkable thing about this solution is that it doesn't fill the whole domain, even though you're putting energy into the system everywhere. And what you see is that, because when the convection sets in, the contours of concentration, which are shown in this panel, are deformed by the motion. And in fact, the concentration is mixed in this region of closed contours. Okay, that's a well-known phenomenon. And so you get this kind of homogenization of the concentration where the localized structure is. And outside, you have this essentially laminar state with no motion at all. Okay, so this localized convecting state is embedded in a laminar background state. Okay. And what is interesting about this is that there are, in fact, two different types of these structures that exist at the same parameter values, both simultaneously stable, and they differ in their symmetry properties. So, for example, this one you see that you have a roll that does something like this over here, and you have a roll that does something in the same direction. So the vortices at the two ends rotate in the same direction. I'm going to call it an odd parity state. And then we also have even parity states where the roll rotates this way, but it rotates at the other end in the opposite direction. So the whole structure has reflection symmetry about the midplane. And in fact, it turns out there is a very, very large number of these simultaneously stable solutions at this one parameter value. One of the reasons I'd like to explain, first of all, why these exist, these kind of solutions exist, and why you have so many different coexisting solutions. Of course, in an experiment, which one would you see? Well, it would depend on how you did the experiment. So one way to do the experiment is this. So you just run a direct numerical simulation. I'm going to show equations later on, but let's just look at some pictures. So I'm plotting horizontal coordinate along the x-axis, and time increasing upwards along the vertical axis. So this is a space-time plot of the solution. The initial state in this system is a state of spatial temporal chaos, complicated motion. It's called dispersive chaos, has been studied by many people. But at this particular value of the parameter, which measures the temperature difference imposed across the layer, this state of chaotic motion is itself unstable in a kind of focusing instability, and it produces this kind of structure which is almost stationary, as you can see, and when it forms, it suppresses the motion outside. Now, this structure isn't a stationary state in this case. If you continue it for a longer time, eventually these cells at the end are gradually eroded. The system collapses back into this chaotic state. And of course, the chaotic state is unstable to this focusing instability, so the whole thing happens over again, right? Perhaps in a different location. And you end up with a situation that is shown in the next slide. You get kind of relaxation oscillations. This is a measure of the heat transport across the layer as a function of time horizontally. And what you see here is these intervals of the spatial temporal chaos. Here is the focusing instability, produces the localized structure, then it gets slowly eroded over time. As it's losing rolls, right, the heat transport decreases, collapses back into the spatial temporal chaos, and the whole thing repeats again in some kind of irregular fashion. Well, if you change the parameter value from 1774 to 1775, you still get the instability, but now the structure that is formed remains stable. And it remains stable for as long as you like. And of course, it can be anywhere in this domain because I'm using periodic boundary conditions. So that's how these structures actually form in this particular situation. In other situations, they may form differently. But once you find them, you can then use these steady localized structures to initialize numerical continuation, and you can follow them through parameter space. And when you do that, you find that they lie on these intertwined branches. There are two branches, one for the odd parity solutions, one for the even parity solutions. And the solutions I showed you at the beginning came from somewhere in this region, from each type from each branch. Okay, so these are all solutions corresponding to stationary spatial localized structures, and many of those are numerically stable, as I will show. There are many other things in this diagram which we're going to talk about later on, but the relaxation oscillations that we saw at the beginning occur somewhere along here. The primary instability occurs at this value of the parameter r. Here is the spatial temporal chaos. These dots just represent time ravages of the heat transport because it's a chaotic state. And the focusing instability that gives rise to these localized structures occurs somewhere in the vicinity of this region here, and here they're finally formed. And so we're going to talk about various aspects of this picture as we go along. Okay, so let me use that as a motivation for what we're going to talk about. I'm going to use one other experiment as motivation, which I find is very appropriate, and this is an experiment done in Bayreuth by Reinhard Richter, and it's on a ferrofluid. So you take a petri dish, you fill it with the ferrofluid. That's a suspension of little small magnetic particles with a surfactant of their own clump and so on. There are a lot of experimental details, but you apply a nominally uniform vertical magnetic field to the system. That's shown here along the horizontal axis. And then as you increase this uniform magnetic field that's applied across the system, you find that the undeformed surface loses stability, and the system transitions to a state with a hexagonal structure of peaks. There are a lot of defects, of course, that are present because this is an uncontrolled situation. As you increase the magnetic field some further, the defects heal. You get an almost perfectly hexagonal pattern. And then if you decrease the magnetic field again, you follow this branch over here. And then eventually, when the magnetic field strength is too little, the peaks disappear into the flat interface, and the flat interface is restored. Okay, so you have this nice hysteresis loop. Now, inside this hysteresis loop, which, by the way, is similar to what we saw in the previous bifurcation diagram, there is here a hysteresis loop between convection. This is the stationary overturning convection that fills the whole domain, and of course the conduction state for which the Nusselt number equals to 1, and that corresponds to this axis. So just like in this example, in the ferrofluid experiment also has a large hysteresis loop, and in some subregion of that, for example here, you find that you can construct lots of solutions that are simultaneously, or lots of states which are simultaneously stable. And the way you do that is by applying a finite amplitude perturbation. So you take a bar magnet, you bring it towards the surface, you pull out a peak, you remove the bar magnet, and if the ambient magnetic field strength is right, the peak just remains sitting there. Doesn't collapse back. Okay, so that's a finite amplitude perturbation that you've applied. And of course, you can do it again, right? You bring the bar magnet to a different part of the fluid, you pull out a peak, you remove it, the peak stays there, right? So you have this possibility of creating a very large number of simultaneously stable solutions. And of course, which ones you will see will depend on how you do the experiment, right? Just like in the fluid experiment before. So bear these two examples in mind. Yeah. Oh, this is an edge effect, of course. This is where my assumption that the ambient magnetic field is uniform breaks down because it actually flares out, and that produces that ring of peaks.
Why is there 8?
Oh, here, because, let's see, 1, 2, 3, 4, 5, 6, 7, 8, it's this one.
So it's not hexagonal.
No, these peaks are wherever you like. There's no particular organization. They can form bound states, but you can put them wherever you like. Right? This is inside the hysteresis loop between the flat interface and the hexagonal pattern of peaks. right? But in that region of coexistence, you can create all of these other states, like isolated peaks, for example. Okay, and all of these here have been created at the same parameter value. They're all simultaneously stable. Okay, and the example of an 8-peak structure is shown there. But they can be essentially wherever you like. Not completely wherever you like, but essentially. Okay, so that's so localized structures. I'm going to call them LS. They arise in a lot of applications, particularly in fluid mechanics, but also in reaction diffusion equations and things of that type, buckling problems. There's a whole variety of applications of this structure. Water wave theory, of course. They can exist in 1, 2, or 3 dimensions. They are strongly nonlinear states, and as I indicated, they are generally created not through some local instability, but through a finite amplitude perturbation, right? So you have to think hard about how to access them analytically, because you don't have a small parameter that allows you to find them, you know, in a simple way by looking for instabilities. They can undergo different types of dynamics, splitting, decay, all kinds of things like that. They can spontaneously start to propagate. And of course, defects in patterns, if you demodulate the pattern, remove the pattern, then defects, of course, can be thought of as localized structures as well. And so there's a connection with the properties of defects as well. Okay. So let's me start at a very basic level. So this is a picture that I'm sure everybody here has seen. This is the neutral stability curve for the trivial solution, like a flat interface, for example, in a system that has spatially homogeneous forcing. Okay? And if I take u equals 0 and I perturb it a little bit, I want to know, is it going to be stable, is it going to be unstable? So I'm going to look for solutions that have a growth rate sigma and some wave number k. This is just in 1 dimension. And then I can see along what curve do I have sigma equals 0 corresponding to marginal stability. And typically, in almost all fluid problems, you get a curve that looks like this, where R is the parameter that I'm varying. It could be the temperature difference across the fluid layer. It could be the magnetic field or something like that. And the wave number k is plotted horizontally. Okay? What does this picture mean? It says that if you're above this curve, the growth rate sigma is positive, and so you have instability. U equals 0 is an unstable state. Okay, and it's going to evolve into some nonlinear structure. If you're below that curve, then sigma is negative, and the disturbance will decay, and the U equals 0, the homogeneous state, will be restored. Okay, you've all seen this kind of picture. But let me look at this picture from a slightly different perspective. And that is, I'm going to just look for steady solutions. Right? If I want to look at steady time-independent solutions, that means I'm forced to just look at what happens along the black curve. Right? That's the only place where I have steady solutions of the linear problem. Okay? So imagine now that I take this value of R, and I'm looking for steady solutions. Then I have 2, right? They have different wave numbers, k1 and k2. Imagine now that I take R and I decrease it. Then, as I decrease it, these 2 wave numbers coalesce at this point RC, at the wave number kc, which is the instability threshold in this in the time domain, in the instability way of looking at the problem, right? If I'm looking just at solutions that have a non-zero growth rate, I'm going to imagine that I'm varying R this way. When I reach the minimum, I'll say U has become unstable, and it's become unstable to oscillations or a mode with wave number Kc. But now I'm looking at steady solutions, and I'm decreasing R, and I see that K1 and K2 coalesce at Rc at wave number Kc. So I have actually 2 modes there, double multiplicity with wave number k. And then if I decrease R even more, then I'm going to go below the curve. And what happens? Well, k has to become complex. Right? And that's nice, because if I have complex k, that means that I can have solutions that grow exponentially from u equals 0, and also have solutions that decay exponentially to k equals 0. Right? And so below this point, I can look for localized structures. And that's precisely the region of subcritical instabilities that you saw in the previous pictures. You had the hysteresis loop. Okay? So that's sort of the basic idea. Of course, we want to do this in the nonlinear regime, but I hope this is clear to everybody. So let me just say this a little more technically, not much more technically. So suppose I have some PDE on the real line given by this, with a trivial solution u equals 0, ux equals 0, etc. Okay? Then if I look for steady solutions, I'm going to put the time derivative equal to 0, and I can just look at this equation g equals 0, and that's a dynamical system in space. It's an ordinary differential equation in space, and it has a trivial solution u equals 0 at the origin. Okay? And then if I want to look for spatial localized structures, what I need is that this fixed point 0 is hyperbolic. It has some unstable direction, so I can leave it, and some stable direction, so I can return to it, right? Of course, whether that's possible depends on what happens in the nonlinear regime. But the necessary condition is that O, the fixed point, is an unstable, it's a hyperbolic fixed point with stable, unstable directions of this dynamical system, g equals 0. Okay? So let's linearize this problem, this one here, and we're going to look for solutions that go in space, like e to the lambda x, not in time, but in space. And once I do that, I can look at the linearized problem, substitute this into here, and I get a condition that has to be satisfied by the spatial eigenvalues lambda. Okay, some polynomial p of lambda equals 0 in the simplest case. Okay. And now g is real valued, so what I know is that if p of lambda is 0, then p of lambda bar also has to be 0. And if the system is reversible in space, that means that it's left-right invariant. That's the situation under which I can get stationary instability. If the system is not left-right invariant, the generic bifurcation at onset is a Hopf bifurcation. You're going to get traveling waves, right? So if I'm talking about a reversible system with symmetry under x goes to minus x, then if p of lambda is equal to 0, then p of minus lambda is also 0. Right? Because I just change x to minus x. And that means that if I have a complex eigenvalue lambda, then it actually comes in a quartet, right? Because lambda bar is also an eigenvalue, and minus lambda and minus lambda bar are all eigenvalues, right? So I have 4 eigenvalues. So this kind of a situation can happen in 4-dimensional problems in space or higher, but not in lower dimensional problems. Okay? And I mentioned that Professor Tolan was one of the people who've exploited this observation in the context of water waves a long time ago in 1993, and then Alan Champness has developed this much further, and so have many other people. So here's a picture from a paper by Woods and Champness, just looking at a quadratic equation. Quadratic equations are nice because we can solve them. And so here I'm plotting the root structure of this equation in the AB plane. And above this parabola over here, you see I have the quartet of eigenvalues, complex eigenvalues that I mentioned. Okay? When I go this way, these eigenvalues collide on the imaginary axis, and so along curve C2, I have a pair of purely imaginary eigenvalues of double multiplicity. Okay? And then when I cross the curve, I end up here with a pair of positive imaginary part eigenvalues and, of course, negative imaginary part eigenvalues. So this is the situation. You know, lambda is ik1, ik2, right? Here are the wave numbers k1 and k2 I've mentioned. As I go in this direction, they coalesce on the imaginary axis at one particular wave number. That's the critical wave number. And when I go below the critical value of R, then they split and become complex, right? That's exactly the picture that I was talking about in an earlier slide, okay? Just shown in a different way. And of course, other things happen in other parts of the diagram, but I'm going to be mostly interested here in this transition. This two eigenvalues colliding on the imaginary axis and then splitting and going off into the complex plane. A couple of remarks about dimensions of certain manifolds. These are invariant structures in this phase space of the problem. And it's useful to think about dimensions. So if I have an equilibrium O and it's hyperbolic, then it has some unstable directions and some stable directions. And in the linearized problem, those span the stable and unstable eigenspaces, right? In the nonlinear regime, of course, you have the analog of these linear eigenspaces. They're called manifolds. They're invariant under the spatial dynamics of the problem. They are tangent to the eigenspaces. And they are invariant under dynamics, as I've already said. Okay? So, for example, if I have a two-dimensional unstable manifold of O, that means that I have two unstable directions. Okay? And that was the example in the previous slide, where I have two eigenvalues which were in the positive half plane. Okay? So suppose I have n equals 4. So that's the simplest situation that we need, right, to get this kind of a situation. Then we may suppose that the equilibrium has two stable directions and two unstable directions. And we may be interested in trying to see whether we can get intersections of a two-dimensional unstable manifold with a two-dimensional stable manifold, right? So we can go this way in 4 dimensions. Right? In general, that's hard to think about because at least I can't think about 4 dimensions very easily. But if you think about intersection of two one-dimensional manifolds in 3 dimensions, it's a little bit easier, right? And in general, they will not intersect. You have to play with the parameter to actually make them intersect, so you can actually go from the origin back to the origin, right? But if you have symmetry in the problem, like this reversibility symmetry, this is not true, because if you have, you can take the manifold from O, it goes to a plane which is left invariant by the reversibility, S goes to minus X. That's a 3-dimensional surface. The intersection of a 2-dimensional manifold with a 3-dimensional surface in 4 dimensions is structurally stable. You can get the rest of the solution just by reflecting in that plane, and now the solution becomes structurally stable. So you get so-called homoclinic orbits, solitary waves, or wherever you like them, because of the presence of the symmetry X goes to minus X in the problem. They persist under variations of the parameter. If I had two different fixed points, O and P, I can also look at connections between O and P. Those are called fronts. And same argument. Suppose this is 2-dimensional. The unstable manifold is 2-dimensional. The stable manifold of P is 2-dimensional. I'm going to see intersections in 4 dimensions. In general, I have to tune a parameter to have a solution like that. Same argument. And that means I only expect to see stationary fronts at a single parameter value. Okay? Of course, if I change the parameter value, I expect the fronts to move. Suppose now that G equals 0 has a periodic orbit, UP of X, which is invariant under reflection, X goes to minus X. Right? Then, because of this reversibility symmetry, in 4 dimensions, this orbit is going to have one unstable direction in one stable direction, given by the unstable Floquet multiplier and the stable Floquet multiplier. And there's going to be a double zero eigenvalue. Why double zero eigenvalue? Because you have 1, 0, which corresponds to phase invariance. You can just go around the periodic orbit without changing the solution, right? The X goes to minus X symmetry of the problem doubles that zero exponent or Floquet multiply 1. So you get 2 neutrally stable directions. So that means that the center stable manifold of UP is 3-dimensional. 3-dimensional, 1 dimension higher, right? Because I have you know, I'm coming in, and then I have these two other dimensions around, right? So it's a three-dimensional stable manifold of the periodic orbit. And now the intersection of a two-dimensional unstable manifold of O and this three-dimensional center stable manifold of UP, the periodic orbit, is structurally stable in 4 dimensions. And that means that those intersections will persist under parameter changes. And of course, if I have a situation like this, then I can, once I have the connection between O and the periodic orbit, I can go from the periodic orbit back to O just by reflection. And so I actually have what's called a heteroconic cycle, a connection between an equilibrium, periodic orbit, back to the same equilibrium. And that structure is structurally stable under perturbations in parameter. So that's a useful observation, and we'll make use of that as we go along. Okay, so let's start with the simplest example I know of this type. This is the Swift-Homburg equation that's written here. It's first order in time. On the real line, of course, it's just first order in space. The important thing is that it has a fourth order a derivative in x for reasons I've already explained. It's reversible under x. X goes to minus x is the symmetry of this problem. There's a parameter called r that's going to be the bifurcation parameter I'm going to vary. And finally, there is some nonlinearity here, which I'm going to pick to produce this hysteresis loop that we saw in the pictures at the beginning. Okay? So I'm basically going to make this problem look like the experiments I showed you. Okay? So for example, I can pick a destabilizing quadratic term, and whoops, there's a mistake here, and a stabilizing cubic term. U cubed, sorry. Now, this equation has certain special properties. It has very simple dynamics in time. It's a gradient system in time. And the Lyapunov function, which I'm going to call the free energy of the system, F, is given by this expression over here. Okay, and that means that on finite domains, the system evolves to equilibrium. In fact, at every point, it evolves to a stationary solution. And the local minima of F are going to correspond to stable solutions. Local maxima are going to correspond to unstable solutions. So really what we want to know is understand the energy landscape generated by this functional F. Okay, so that's the basic idea. So let's do what I've just indicated. We're going to look for steady solutions of that equation. So we have an ODE, this one. And I'm going to be interested first in looking at the stability of u equals 0. That's a trivial solution. So I linearize the equation, and that means I'm going to drop this nonlinear term. I'm going to look for these spatially growing solutions with growth rate lambda in space, and then lambda satisfies this quadratic equation. Okay, and here are the solutions of this equation for different values of r. At r equals 0, I have these double multiplicity eigenvalues on the imaginary axis. For lambda, for r less than 0, they split and move it off the imaginary axis into the complex plane. So I have a two-dimensional unstable manifold, a two-dimensional stable manifold. If, on the other hand, r is positive, then the eigenvalues split but remain on the imaginary axis. And so I have these wave numbers k1 and k2. So will that make sense? The important observation here is that when r is small and negative, this distance here is of order square root of r, or minus r. Okay, so the splitting is very small, and that means that the growth rate in space, right, given by the real part of lambda, is going to be very weak. So what do I expect to see? I expect to see something that oscillates with a wave number close to kc, right? That's just given by the imaginary part here. And then it's going to be modulated in space over a large length scale. The length scale given by 1 over square root of minus r. Right? This picture tells me that. So what I'm going to do now is I'm going to make use of that. And what I want to do is to show you that you can, in fact, get a connection in the nonlinear regime over here under these circumstances that I've described. In other words, I'm going to have an unstable, I'm departing from u equals 0 exponentially, at the growth rate I've just calculated. I'm going to do something over here and connect to a stable direction that goes back to u equals 0 as x goes to plus infinity. Okay? And to do that, I'm going to use the method of multiple scales, which I hope is familiar to people here. But and for reasons I'll explain, I'm going to do it to fifth order. I mean, this is a summer school, so you know schools are hard, so we have to do just a couple of slides of a calculation. But the basic idea is the following. I'm going to look at small negative values of r, okay? And I'm going to look for a solution that is small in amplitude of size epsilon. Epsilon is given by this. And the solution depends on a fast length scale and this modulation length scale capital X given by epsilon x plus dot dot dot. And u1 is going to have some amplitude that varies slowly in space. And then I have the fast oscillation given by the critical wave number at the instability, right? At r equals 0. That's the imaginary part of lambda at r equals 0. Okay, and I'm going to do it for the cubic quintic equation because it's easier. Just to show you how this calculation goes, okay? So what do we do? Well, wherever we have d by dx, we're going to replace it by partial d by d little x plus epsilon d by d capital X. And then we're going to treat the slow scales and the fast scales as independent parameters. That, of course, is a bit of a swindle. One has to be careful about this. But if you are, then you can trust the solutions under appropriate conditions. And so I'm just going to substitute this ansatz into the equations. I'm going to put r equals 0. And I'll see what I get order by order in epsilon. And here are the equations written out in gory detail. Don't pay attention to this. I think this is being recorded, so you can get these equations later if you want. But the basic point is that the u1 and u2 equations are just solved by some arbitrary amplitude a1 times the fast oscillation plus complex conjugate, of course, because it's a real value problem, and similarly for u2. At order 3, epsilon cubed, I have an arbitrary homogeneous solution, again with spatial frequency of wave number qc and an amplitude a3 plus an inhomogeneous term that's generated from u1 and u2. And the solvability condition that you have to apply at order epsilon 3 gives you an equation for the evolution of a1. That's this guy over here. And if this condition is imposed, then you can solve for a3 and continue the process. Okay, this is how these methods work. Okay, I don't want to get into details of this, but you continue this, you go to u4, you get an equation for a2, that's this guy over here. And finally, at fifth order, you get a solvability condition for this a5, and that gives you an equation that looks something like this. Right? So this is the equation for the slow evolution of the amplitude a1. Right? So that's the leading order description of the solution. And what I do next is that I take a1 and combine it with a2 and a3 in this way to get, because these other terms, you know, also modulate the same e to the I qcx, right? So I'm looking at the total amplitude of all of those contributions, and I call that z. Since I'm in England, I have to call it z. And then I get an equation that looks like this. There are some high-order derivatives in here, but I can get rid of them because I can just use this, right, differentiate a couple of times to get rid of this guy. So by iteration, I can end up finally with this evolution equation in space for the slow spatial dependence of this amplitude of the mode e to the I kcx. Okay? So why did I do this? I did it because I want to make contact with the normal form for the reversible one-to-one Hopf bifurcation. So this is a resonant remember those two wave numbers, k1 and k2? right? They came together as I decrease r, and then they collided at the onset of instability, right, at the critical parameter value, and then we had eigenvalues of double multiplicity. Remember that? Spatial eigenvalues of double multiplicity. So people sometimes call that the one-to-one spatial resonance, because these two wave numbers come together in one-to-one resonance. They call it the Hopf bifurcation because it's an oscillation in space, but not in time, but it doesn't matter, okay? All right, and it's reversible, right, because of this x goes to minus x symmetry, right? So the normal form for that was derived by Jos and Perouem a number of years ago, and it takes this form for amplitudes A and B, where P and Q are polynomials in something called y, which is the modulus of a squared, and something called w, which is given by this. Okay, I don't want to discuss the derivation of this, but I do want to point out that these P and Q are arbitrary, and so I can just expand them in a Taylor series. And I've kept here a term in mu. Mu is the bifurcation parameter, and then I have all these other terms from the Taylor series of P and Q. Now, it turns out this normal form and what I've just done are in fact the same thing, and so the calculation I've just performed actually allows me to compute coefficients in the normal form, and then to use what I know about the normal form to make certain deductions about what happens in the nonlinear regime near this r equals 0 instability. Okay? And so how do I do that? Well, it's usual to first put mu equals 0, so you work right at the bifurcation. Then we do some nonlinear calculations, and then we add back the effects of mu not equal to 0. It's called unfolding of a bifurcation. So I'm not going to do this in a kind of serious way, but the basic idea is that I want to take A and B, and I want to decompose them into the slow and fast variables, exactly as I did before for my Swift-Homburg equation. And when I do that, so I have to, turns out I have to do this. And when I do that and I substitute this into here, then I end up with these equations where I've dropped the tildes, okay? And what you see is that this equation, for example, at leading order tells me that B is A prime plus terms of order epsilon, and so on. So by iteration, I can construct an equation just for A. So I can eliminate B from the second equation. And when I do that, here is the actual equation for B, and here is my final equation. And it has exactly the same form as that equation for Z, capital Z, that I derived earlier. And by comparing the equations after a little nonlinear near identity change of variables, I can get coefficients in the normal form, right? So that's kind of calculation that one needs to do if one wants to know what happens near the onset at r equals 0, but let me show you in pictures what it means. Well, sorry, there's one more slide. And this is putting it back the bifurcation parameter mu in this way, and if I look at the effect of mu in the Z equation, Z equation, and in the A equation, I can also get the coefficients P1 and Q1 in the normal form. Okay. So the normal form is completely integrable. There are two conserved quantities. You can think of this as a Hamiltonian, H, and there's something like an angular momentum. The reason there are two conserved quantities is because there are two continuous symmetries in this problem. One is translation invariance. The other is something called a normal form invariance. It has to do with the normal form transformations that are used to generate the Jos-Perouem normal form. The nice thing about having these two constants of motion is that I can take my equation and I can reduce it to just an equation for a particle in a potential. And we all know how to look at the motions of a particle in a potential. So here is an effective potential V. It's given in terms of the quantities I've computed, namely, remember, fifth order calculation, Q4. I needed to know Q4 to get the potential. That's why I had to go to fifth order in the calculation. I want to solve this for A. And since little a is the modulus of A squared, it has to be positive. So I'm only interested in positive solutions of this equation. Okay? So So some pictures. So what's shown here is the parameter mu and Q2. That was one of the cubic coefficients that are computed in the previous calculation. And in different regions of this Q2 mu plane, I have different shapes of the potential, and here they're shown. So for example, in this region here, I have a potential that looks something like this. This is A plotted this way, horizontally, V plotted vertically. And what you see here is that I have a nice homoclinic orbit. I go from the origin outward, I hit the potential, I bounce back, return to the origin, right? That's a great homoclinic orbit. That's a localized state. Right? Likewise over here. So I have lots of localized states in this region here. More interesting, actually, is the second case. This is where Q4 is positive, because there I can get a situation where the peak at the origin and the peak away from the origin are at the same height. So I have a connection from the origin to a non-zero A, but non-zero A means a periodic orbit, right? Because the amplitude A times e to the I QCX, right? So I have a connection between the origin and a periodic orbit and back to the origin, right? That's one of these heteroclinic cycles that I already mentioned. Okay? And that occurs along a particular curve that you can compute from the potential mu equals mu star. And below that curve, there are homoclinic orbits that accumulate on that heteroclinic orbit. Okay? That's basically this picture here. I have solution at the origin and go here, bounce back to the origin, right? Okay? So that kind of tells me what are all the possible solutions near r equals 0 in the nonlinear regime. So let's just look at this a little more closely. So let me just truncate now at the leading nonlinearity. So I have an equation that looks like this. This is steady state real Ginzburg-Landau equation, right? There are two types of solutions of this. If mu2 is positive, mu2 positive means r is less than 0, right? So I'm on the subcritical part of the bifurcation diagram. And in this case, I can have a solution that looks like this. This is just a constant. And so z is just a constant. And it corresponds to u of x. If I go back to the original description, u of x is just a periodic wave train with an amplitude that goes like the square root of r. And there is an arbitrary phase here because I can take my periodic oscillation, I can translate it arbitrarily in the horizontal. Okay, so that's one type of solution. Because we knew about periodic solutions bifurcating at r equals 0. I mean, after all, it's a half bifurcation, right? But there is another type of solution where z has a Sech-like profile, and that corresponds to the following solution. Again, I have a periodic wave train, but now there is an envelope that varies on the slow spatial scale, square root of minus r, right? And the amplitude also goes like square root of r, okay? So what have I done? So I have found two types of solutions, both of which appear at r equals 0. Periodic solutions and localized solutions appear simultaneously at r equals 0. Now it looks like there are lots of different localized structures because it looks like this phi is also arbitrary, but in this case it's not. And this is where the use of the or the treatment of the fast and slow spatial variables, independent variables, breaks down. Because here I can't move the envelope arbitrarily relative to the periodic wave train. I can't do it because the wave train, because the envelope is not constant. And so only certain values of phi are permitted. And it turns out that the picture looks something like this. What is drawn here is phi is defined up modulo 2 pi, so it lives on a circle, right? And for the 2, 3, the quadratic cubic Swift-Homburg equation, there are two values of phi that are permitted, 0 and pi. And if you take the cubic quintic Swift-Homburg equation, there are 4 values of phi that are permitted, that are chosen out of the the circle of phi's. And that selection process is a little complicated. You have to do beyond all orders asymptotic, exponential asymptotic. So I'm not going to do that here, but it's easy to check that the solutions with phi equals 0 and phi equals pi, for example, do in fact satisfy the equation. And if you try to do it with a different value of phi, you're going to run into problems. So you can kind of look at it backwards that way. So let's see how this works in a fluid problem. I'm not going to write down equations for now, but I'm going to look at binary convection, binary mixture convection in a porous medium. It's just that as an example. So again, I'm take a layer, two-dimensional layer. I'm going to heat it from below. The layer is specified by something called the separation ratio that measures how the two components separate in an imposed temperature gradient. That's a dimensionless parameter proportional to the Sorey coefficient. And then I have the bifurcation parameter R that measures the temperature difference across the system. And here is the usual neutral stability curve, stable below, unstable above. Okay. But if you look at it from my point of view, what you would do is you would take the equations for a temperature perturbation and concentration perturbation. You look for solutions that grow in space. You solve the steady problem, linearized, about the conduction solution, and allow lambda to be complex, right? That's how we do this problem. It's a little more complicated here because I have also boundary conditions in the vertical, right? So it's now actually a boundary value problem at every value of R, but I can solve it, okay? The size of the eigenvalue problem is double, right? Because my wave number has real and imaginary parts. So the quantities are all complex now. But it doesn't matter. I find that a particular value of R, or the Rayleigh number, given by this, I have purely imaginary eigenvalues of double multiplicity, right? And then if I decrease Ra a little bit, then they go from the imaginary axis. They split by the square root of Rayleigh number minus Rayleigh critical. You get the quartet of eigenvalues. On the other hand, if I increase the Rayleigh number a little bit, they split but remain on the imaginary axis. Okay? Exactly what we saw in the Swift-Homburg equation, because here there's an infinite number of eigenvalues, right? In this kind of a problem, but all the other ones are more negative, and you can argue that they are not important for the purpose of generating localized structure. And then if you calculate the periodic solutions, they bifurcate subcritically. So you're in this situation where you have the right sign of this coefficient Q2 in the normal form, and so you can look at you can look for localized structures. So this is the kind of thing that you can do for a fluid problem, just to see that you have the same bifurcation structure. And once you have that same bifurcation structure, this weakly nonlinear theory I've just described, that applies directly to a fluid problem. Okay, so what have we done? So far, we've been very lazy. We've just looked near R equals 0, which is this point, right? We've analyzed that primary instability, and we saw that we produce subcritically some periodic solutions in red here. They're unstable all the way up to a fold here, and where they acquire stability, right? And then we also saw that for the 2-3 case, we had a pair of localized solutions that bifurcate simultaneously with the periodic solutions at R equals 0, the phi equals 0 solutions and the phi equals pi solutions, right? And they, if you follow them numerically, here they are. And what do they look like? Well, the phi equals 0 solutions have a peak in the middle. They're nicely localized. The phi equals pi solutions have a dip in the middle. That's one way of telling them apart, okay? Okay, and the L0 branch consists of solutions with peaks in the middle. The L pi branch consists of solutions with a dip in the middle. Okay, solutions are left-right symmetric, and if you follow them, you find that they enter the shaded region. The shaded region I'm going to call the snaking region, or pinning region, for reasons I'll explain, where these branches start to go back and forth across the region, and in the process of oscillating, you see that the structure acquires extra oscillations at the end, like this. So this shows the solution at this point, at this point, at this point. As you go up this structure, the localized structure adds oscillations at the end, and this the localized structure grows in extent. It's trying to approach the periodic solution that lies up here. If you look at this, of course, I should also mention is that the solid lines indicate stability. I'll talk about that in a moment. And you see that in this region, which is inside the hysteresis loop, you have an arbitrary number of coexisting stable solutions of either type, right? The ones with the peak in the middle and ones with a dip in the middle. So that's the thing we were looking for, right? So the way you get to this region is by going very far away, doing something that looks very irrelevant, but finally it allows you to discover the region that you're actually interested in, the one with the localized solution. If you look at this in a little more detail, you see that in addition there are branches of asymmetric solutions, like these ones here, that interconnect the solutions L0 and L pi. And those asymmetric solutions are shown over here as you go across the structure. In this particular problem, these correspond to stationary solutions, but in systems that do not have gradient structure, like fluid problems, asymmetric solutions all travel. So these would be moving localized structures. In this particular example, they're all unstable. So how do we do the stability? Well, we just solve the linear problem for these localized solutions. So here is the localized solution is called U of x here. And we linearize about U of x. And we have to solve an eigenvalue problem for the growth rate of the instability. And that is shown over here as a function of r, or actually the arc length along the curve. So here is the growth rate. And you see, for example, that the L0 solutions are initially unstable in amplitude. Amplitude eigenvalue increases. Then it crosses 0 at the first fold, is stable, crosses back at the second fold, and so on. And the phase eigenvalue asymptotically approaches the behavior of the amplitude eigenvalue. And the kind of the opposite thing happens for the phase eigenvalue for the L pi solution. This is exactly what we saw in the previous picture, where you have an unstable amplitude eigenvalue, fold becomes stable, fold becomes unstable, right? So that's where the stability assignments go through. And of course, at the fold, you have to have a 0 eigenvalue. That's a simple theorem. And here are the corresponding eigenfunctions. Here is the localized state, U of x, that I'm looking at. The amplitude eigenfunction is symmetric. It has peaks at the location of the fronts that connect the localized structure to the background state. The phase eigenvalue is antisymmetric. It produces asymmetric solution. 3 minutes. Okay. I thought I have hour and a half.
Wait.
No? I'm happy to end.
Certainly.
Okay. I see Uwe's bored already. Okay, I'll speed up. Okay, and then there is another, right? So these eigenfunctions change the stability at the folds of this curve. These eigenfunctions generate the asymmetric solutions that I showed you in the previous picture. And then there is always a neutral mode, the so-called Goldstone mode, that just corresponds to translation of the pattern, right? And that eigenfunction is just given by the derivative of U of x. So if I have this situation, so here is what would happen if I put this into a finite domain, finite but periodic domain, say, but large. Now what happens is that this bifurcation that we talked about breaks up. And that's because the localized structure doesn't quite fit into the domain. And so this bifurcation to localized states becomes a secondary bifurcation from the periodic solutions at small amplitude. And I think that's one of the reasons people haven't really understood where localized states come from. It's because if you put the system in a periodic box, you have to know the periodic solutions first, look at their stability, and then find this bifurcation that produces the localized state. This is a funny situation where actually putting the system on the real line is much easier than using periodic boundary conditions. Because on the real line, you get this multiple bifurcation from the trivial solution, u equals 0, and you can do all these calculations that I've just described. Now, the other interesting thing about this is that, you know, this thing snakes, because it can't snake forever if it's in a finite box. Eventually, the structure is going to fill the box, and then you can't add any more oscillations. And so what it does, it exits this snaking or pinning region and terminates near the fold of the periodic solution. And right here, the solution resembles, well, what does it resemble? It resembles a hole in an otherwise periodic solution. Right? So the branch actually connects holes in a periodic solution with localized states that are connected to u equals 0. On the whole real line, of course, those two branches would be disconnected. The holes would snake in the same region, and as the spatial localized structures, they bifurcate from r equals 0. And of course, once you have a single pulse, called these single pulse localized structures, I can also get multi-pulse solutions, like these two-pulse solutions. These are all equally spaced. Remember, it's a periodic domain, so these are all equally spaced. So you get just half as many oscillations, which is basically snaking in a domain of half the size. But you can also get bound states of these localized structures that look like this. They live on isolas in the bifurcation diagram. I should have said that this is the norm of the solution in the vertical. And so, depending on their separation, I have a branch of solutions like this, or like this. Okay? The separations are quantized in half the wavelength of the basic oscillation, 2 pi over qc. As you can see here, you have a peak here, you have a minimum here, and so on. And you can get localized structures. Well, like in this isola, you have a bound state of single peak structures. On this one, you have bound states of 2 peak structures. Here you have bound states of 3 peak structures. All of this lives in the same shaded region of the bifurcation diagram. So you can see there's a whole enormous zoo of different possible solutions. And I haven't really begun explaining what or describing what all the possible solutions are, because you can also get things like this. You know, bound states of different solutions, and if you have bound states of 2, 1, or 3, right? And all of those different types of solutions live in this shaded region that are identified through this process. So why are there all these solutions? So let's think about it in 2 different ways. One, a mathematical way. And so this is a geometrical picture, originally I think due to Woods and Champness. So the basic idea is the following. We're going to look in our 4-dimensional phase space, and in that 4-dimensional phase space, there's going to be a plane within which solutions are reflection symmetric. Okay, if a solution lies in that plane, it'll be reflection symmetric. If it lies off the plane, then of course under reflection, it'll go below the plane, right? That's the idea. So we have an equilibrium, which is the origin. It's hyperbolic, so that's going to be this spot here. And then this corresponds to the periodic orbit. So how do we do the calculation? Well, actually, for the Swift-Homburg, this is not so hard, because the Swift-Homburg actually is a Hamiltonian system in space. Why? Because the free function, the free energy is like a Lyapunov function. Once you have a Lyapunov function, you can use it like a Lagrangian, and from the Lagrangian, you can construct a Hamiltonian, right? So the Swift-Homburg equation is Hamiltonian. So you can look at the energy surface that contains the fixed point and the periodic orbit, right? They have the same energy. So I'm going to call that the Maxwell point. Okay, here it would correspond to the h equals 0 surface level curve of the Hamiltonian. So that drops my dimension from 4 to 3. Now I have a periodic orbit in h equals 0, right? But I can look at a time 1 map of that, right? Where 1 is the period of the orbit in space, the wavelength of the orbit. And so I go from 3 to 2 dimensions, and now I can already draw a picture, right? And of course, the periodic orbit now becomes a fixed point of this discrete map. Is everybody with me? So when I do that, I have the original equilibrium at the origin. I have the periodic orbit over here. They're symmetric, so they lie on that green curve. And I can look at their stable and unstable manifolds, right? Things I've already talked about. And so in blue are the stable and unstable manifolds of the origin. That's U equals 0, the homogeneous state. In red are the corresponding manifolds for the periodic orbit. You know, those center stable manifolds that I talked about, okay? And the left folds of the snaking diagram correspond to the first tangency between the unstable manifold of the origin and the stable manifold of the periodic orbit. The right folds correspond to the last tangency between those manifolds. And in between, I have transversal intersections of these manifolds, so I have structurally stable solutions. And it's interesting to look at the intersections of these manifolds. For example, here, by symmetry, you see if I have a solution over here, I can run it backwards and it came from here, but by symmetry, I also have exactly the same thing going in the opposite direction, right? So if I have an intersection on the green curve that corresponds to a localized state, that's homoclinic to the origin. And because this is a homoclinic tangle, I'm going to have lots of intersections, right? Okay? And once I have, in addition to those intersections, I also have these subsidiary intersections like these ones. And they correspond to the asymmetric solutions that we saw that form the rungs of the snakes and lattice structure. Okay, so this is one kind of nice way of thinking about where all of these solutions come from these homoclinic tangles. But I prefer to think about this from a physics point of view. That's in terms of the Maxwell point that I've already mentioned. So here is the value of R at which the periodic solution has the same energy as U equals 0. Right? The two states have the same energy. And it's useful to think about what's going on from the point of view of phase transitions in a system like this. So you know that if I have two homogeneous equilibria, let's call them 1 and 2, could be liquid and a gas or something like that, right? Then if I'm at the critical temperature, 100 degrees, then I can put an interface anywhere between those two, and it doesn't cost me any energy. So I can get lots of localized states with, liquid, gas, right? Doesn't cost me energy. And because the energies are the same, those fronts will remain stationary. We already talked about why they became stationary. It's this codimension 1 business. Okay? But as soon as I change the temperature away from the critical temperature, the fronts are going to move, as I already mentioned, right? And they will move in such a way that the system decreases its energy. So for example, if I increase the temperature by 100 degrees, right, the liquid is going to evaporate, right, and all the fronts going to move in and eliminate the liquid phase, right? And conversely, if I decrease the temperature below 100 degrees, the vapor is going to condense, and the fronts are going to move this way, allowing the liquid phase to invade the domain. Okay? So that's the usual picture of a phase transition at a critical temperature, say. But we don't, in this problem, we are not dealing with two homogeneous phases. In our problem, one phase is homogeneous, U equals 0, but the other phase is a crystalline phase. It's structured in space, right? And so our fronts are not free to move as soon as the temperature changes away from the Maxwell temperature. Because the front is pinned to the potential behind it, right? And so what happens if I change the temperature away from the critical temperature, the fronts are going to try to, say, move outwards, stretching the structure. But they are pinned, and so you still have a stationary solution, even for a temperature that is not equal to the maximum temperature. You have to change the temperature by a finite amount before the fronts depin and the structure starts to expand. Condensation starts to take place. Okay? So you can think of all of what I've talked about really in terms of just standard phase transitions. Just one of the phases is structured in space, and it essentially unfolds the Maxwell point into this very complicated region containing all these different solutions that I've described. Okay? Well, so here is just a few things about the fronts. So there are actually two types of fronts. I've drawn them here and here. And of course, you can put them back to back. So you have C1 and C1 of minus x, right? You get a symmetric solution. You can do the same thing for C2. That way you get the L0, L pi solutions. And then if you put back to back C1 and C2, you get the asymmetric solutions, right? That's kind of, so you can think of all the solutions I've talked about really as bound states of these fronts that are the connections between the periodic structure and the homogeneous state U equals 0. Just to convince you that our intuition is correct about this, I've computed here the wavelength of the localized structure between the fronts and different values of R inside the snaking or pinning region. And you can see that below the Maxwell point, the wave number is bigger than at the Maxwell point. That's because the structure is trying to compress, right? Why is it trying to compress? It's because below the Maxwell point, U equals 0 has lower energy than the periodic state, and vice versa for R greater than the Maxwell value. Okay? And so here, the measured values, here is the theory. The theory, it just comes from looking at periodic orbits in the Hamiltonian for the Swift-Hornberg equation in space. So in other words, dH by dx is 0. And I'm looking at the H equals 0 surface that contains the fixed point and the periodic orbit at the Maxwell point. Okay, so let's go now to 2 dimensions. So here is the Swift-Hornberg equation in 2 dimensions. Same equation. Again, 2, 3, or 3, 5. We're going to play the same game as Richter did in his ferrofluid experiment. Remember what he did? He brought the magnet towards the surface. He pulled out a peak, removed the magnet. The peak remained, right? So we can do the same thing here in the plane. So this is x, y. I can make some kind of perturbation in one part of the domain, allow it to evolve, and if I'm in the right parameter regime, it will produce a localized target pattern. Once I have that, I can go somewhere else, introduce a perturbation, allow that to relax, and if I've made the right perturbation, it might produce something like this. Right? I can put another perturbation somewhere else, etc. I can get a spot. Okay? So exactly the same idea. I need to apply finite amplitude perturbation, not infinitesimal. If I apply an infinitesimal perturbation, everything just decays to the homogeneous solution. I have to kick the system, right? Okay? And so in the 3-5 case, I typically get structures of this type. In the 2-3 case, in the quadratic cubic case, I get these structures. And in the cubic quintic case, I get typically structures like this. Hexagons are favored by the quadratic nonlinearity. So let's look at one of these localized states. I'm just going to show now some pictures. So here is a localized state. This is the extended direction. I have Neumann boundary conditions in this direction, right? And this particular solution corresponds to this dot in the parameter plane. So here is my bifurcation parameter mu, again, norm plotted in the vertical direction. Now I can take this solution and I can follow it numerically. And this was done by Daniele Avitabile in Nottingham. And what you find is that if you follow in one direction, it undergoes a Fourier oscillation, and then it produces a branch that does something like this. And the solution at the red dot looks like this. Whereas if I follow it in the opposite direction, it undergoes all these oscillations and produces at the red dot this kind of rug-like state. Okay? So what, why do we, get these things? So over here, if I look at this region here, that's the front that connects the homogeneous state to the structured state behind it. But the structured state is translationally invariant as far as the front is concerned. There can be no pinning of the front, and so no oscillations in the branch. In contrast, over here, here is the front. It sees this oscillation behind it, right? That provides the pinning potential, and that's responsible for the oscillations that you saw in the previous pictures, right? And what's remarkable, in fact, is that a solution like this lies on the same branch as solutions that are really rather different in appearance. How do we think about these solutions? Well, you can think about them from the spatial dynamics perspective, just like in the 1D case. The way we do it is indicated here. So here is my homogeneous state. Here is the periodic state. If I want to look at a front that goes from the homogeneous state to the periodic state, that corresponds to a connection in phase space that does this. If I have a connection that does something like this, what does that correspond to? That corresponds to going from a periodic solution via something back to the periodic state, right? So that's a defect in the periodic state. And we can therefore think of solutions like this as solutions that lie near one of these complicated heteroconic structures that does something like this before returning to the homogeneous state, right? So this is a good way to try to think about these kinds of structures. I just show a few details of how these structures grow along this. You form these dots, and then the dots reconnect into these row-like states or stripe-like states. In the other case, the dots reconnect horizontally, and the structure advances by forming additional dots in front. Okay. So you can study how these structures grow. Let me emphasize one thing. These are all steady solutions, right? Just steady solutions. So equilibria, if you like, of the Swift-Homburg equation. Now, what I've shown you so far were solutions that were even with respect to this, the middle of the structure. There are also solutions that are odd because of the symmetry of the equation. This is the 3-5 equation. And so these are the even solutions. These are the odd solutions. And it won't surprise probably that there are interconnections between the even solutions and the odd solutions. They look something like this. These solutions are asymmetric, but still stationary because this is a gradient system. We can look at the stability of these solutions, and all of these asymmetric solutions are unstable because their eigenvalue, the leading eigenvalues are positive. But we also have connections that go from, say, the even solutions back to the even solutions, and in the middle here, I have a spectrum which lies in the negative half plane, and so those can be stable. We can also get these isolas, like we saw in 1D, isolas of these kind of checkerboard structures. This just shows how the structure depends on where you are on the isola, and then you have a sequence of these isolas with different lengths. Right, all of this again is occurring in this the analog of the pinning region in this two-dimensional problem. And then you get more interesting localized structures that look like these lozenge things. So here's the corresponding bifurcation diagram with the appropriate solution. So here you understand why this thing is not expanding this way, right? Because it's pinned to the oscillations behind it, right? Same reason as before. Because if I had a straight boundary over here, that would just propagate outwards unless I happen to be right at the correct Maxwell point, right? Because there's no pinning if I have a straight interface. But here the interface is not straight, it's actually curved. And so you have this kind of flaring in the local wave number. And that is enough, somehow, I don't know quite how, to pin the structure and prevent the propagation of the front outwards and destroying this structure. And then we have, things like this. We call them worms. Maybe that's not a very good term, but all these things. Some more. The important thing for our purposes later on will be that on one side we have fat worms, and on the other side we have skinny worms. Okay, remember that rule, because I'll talk about that later on. Okay, so this is just a sampling of some of the solutions of a very simple equation. Okay, these ones being localized now in two spatial dimensions. So, of course, there are other kinds of patterns. I just talked about stripes, right? But I can also talk about hexagons and target patterns and spots in 2 dimensions. And if I go into 3 dimensions, there are even more things. So So here is a parameter plane. So this shows the coefficient b2 squared. b2 is the coefficient of the quadratic term in the Swift-Hornberg equation, and this is the bifurcation parameter. It's plotted as minus r. And here you have snaking spots, for example. This actually extends all the way to the axis. It's exponentially thin there because of this. You have to do that exponential, beyond all order exponential asymptotics. Likewise for the localized hexagons in this blue region, and so on. So you have a very complicated situation. This next picture just shows you how the hexagons, localized hexagons, grow as you follow one of these branches. So for example, at location 1, I have a nice regular localized hexagonal pattern of the type you saw earlier. As I follow this in parameter space, like this, you see that I'm adding a cell in the middle of each face. Okay? So the structure nucleates a cell in the middle of each face. And then it adds cells on either side of that face, right? At location 3, by the time I get to location 4, I again have a perfect hexagonal, a localized hexagonal pattern, right? But this one is going to grow differently, right? Because this one has 5 cells aside. This one only has 4 cells aside. So this next one is going to produce spots here first, 2 of them, right? And so on. So these bifurcation diagrams really tell us how structures want to grow. And although I don't know the answer to this, I imagine it picks the location which reduced the energy, by the largest possible amount. I mean, that's a conjecture, at least, that one could make. Okay. So I have 10 minutes. Okay. So maybe if I end earlier, is that okay? Okay. Okay, so I'm just going to introduce the next topic. I'm now going to talk about mesoscopic models of solidification. And the reason I want to talk about that is because models of that type have a very similar structure to what I've just talked about, except for the presence of this extra Laplacian in front. So the right-hand side is the Laplacian of the functional derivative of f with respect to phi, where phi is the simplest possible free energy that you can write down that has an intrinsic length scale, right? And the length scale comes in through this parameter q. And of course, solutions that will minimize the energy are going to have the Laplacian basically canceling the q squared, so they're going to be solutions that have the length scale as close as possible to q, the wave number as close as possible to q. And then I put in the simplest possible nonlinearity, just phi-4, right? And you can derive these models from more complicated, dynamical density function theories. I don't know if Uwe is going to talk about that, but. So the important fact about this is that because of this Laplacian in front, the integral of this order parameter phi is conserved. And what that means physically is that the mass is conserved in the problem. So really the difference between this problem and the previous problem is that I have a conserved quantity, conserved mass. And phi, I've indicated, hopefully, corresponds to density fluctuations about some mean. Right? So I think of phi as oscillating. That would be a crystal. If phi is constant, that would correspond to a liquid. Okay? Is it clear what the interpretation of this is? One has to be a little bit careful with this because this is based really on a gradient expansion, and so it's really more appropriate for structures composed of large molecules, soft matter systems, rather than say, a metal or something like that. But aside from that issue, the dynamics is then, if I substitute this energy into here, is defined by this equation, and so this is what I'm going to call the conserved Swift-Holmberg equation. It has very different properties from what we have described so far, and I'm going to talk about that, I guess, at the beginning of next time. And the reason for that is the conserved mass. And there are many examples in fluid mechanics where the conservation also imposes, or is present and imposes changes on properties of localized structures. One example would be if you take a layer of conducting metal, say, with an imposed vertical magnetic field. That's a problem that's called magnetoconvection. It's been studied by many, many people, especially at Cambridge University. There, the imposed magnetic flux is a conserved quantity. Whatever the flow does, all it's allowed to do is rearrange the magnetic flux. It neither destroys it nor creates it, okay? So in that sense, the conserved quantity there, the magnetic flux, behave very much like the conserved mass in this problem. Conserved mass here being just the integral of phi over the domain. So I know many other examples in fluid mechanics where the conservation of some property also changes the bifurcation diagram. So this is going to be, I think, my last slide. So I'll stay on time. So if I look at this problem in one dimension, this is my equation, right? And if I'm going to look for steady solutions, I just put the left-hand side equal to 0, and then it looks like a trivial problem, and it is a trivial problem. I can integrate twice, right? The first time when I integrate, I'd better take the constant of integration equal to 0, otherwise I'm going to have an inhomogeneous background. But then the second time I integrate, I pick up a constant of integration, which is very important physically, because it's the chemical potential. It acts like the Lagrange multiplier that enforces mass conservation. And then you can imagine that if I look at perturbations for different values of mu, I'm going to get something that it's going to look like the quadratic cubic Swift-Holmberg equation. So there's some connection with the quadratic cubic Swift-Holmberg equation, and the energy that I want to be looking at is this one-dimensional version of the energy that I wrote down on the previous transparency. Okay, so it turns out that in this problem there are lots of localized structures too, and they have to. We believe they are related to the dissolution of a solid or crystalline interface into little bits of solid, that are floating around in the liquid phase, which corresponds to phi equals 0, in an appropriate parameter regime again, corresponding to the pinning-like region. So I'm going to talk about that next time. So maybe I have a few minutes for questions. Is that appropriate? Yeah.
These more exotic localized states in the 2D cases, how did you find them? And did you just start with some plausible perturbations?
They are found essentially like in the first problem I mentioned, this binary fluid convection. You do it just direct numerical simulation, and if you're lucky, you find a stable solution. Once you have one, then you just follow it, right? That's sort of, there's another way to do it that we have also found useful, and that is to do the analysis near r equals 0.
Yeah.
Or whatever, the critical Rayleigh number or something like this. We can do that analysis, and then we know exactly, how the kind of the localized wave packet, what it looks like near r equals 0, even though it has very small amplitude, because we construct it analytically. Once we have that, we can again follow that numerically. So 2 ways. You either do the algebra, or you hope, that your direct, integration in time is going to give you something that's stable.
But were things like the worms directly connected to one of those critical points? The worm states.
Yeah,
Wasn't obvious to me they were.
yeah, the worms. Yeah, I have to look. Sorry. Yeah, and certainly like the spots, the hexagon.
Yeah, yeah.
Yeah, I think the worms. Yeah, that's a good question. Yeah.
So in the 2D case, you could construct basically all the solutions as basically a combination of your two fronts that you just patch together with a different number of pieces in between. So what's equivalent to that in the 2D case?
Yeah. I mean, that also is a good question. I don't think I can really answer that. I mean, you can, of course, get bound states, and they're seen in experiments. You can get, I mean, for example, there are experiments on things called oscillons, which are localized oscillations, say in a parametrically driven, granular layer. And you get, there's a very nice experiment from Harry Sweeney's lab in Austin. You get these localized oscillations where you have a peak at one instant in time, one period of the forcing. Later you have a crater, one period of the forcing, again you have a peak. And these localized structures can form bound states. Over a long time they in fact attract each other and they oscillate out of phase. And they can form chains or kind of molecules consisting of different atoms that oscillate with different phase relations and things of that type. So these kinds of things are observed in a variety of different systems. How to describe them from this perspective is not completely clear, and I'll explain why. The reason is that in 1D, it's completely clear what phase dynamic, or what spatial dynamics mean. Basically, rather than thinking of the problem as a boundary value problem, I think of it as an evolution in X. I start at the equilibrium, I want to do something, and I want to come back to the equilibrium. So space becomes like time. If I have a system in 2D, with 2D unbounded directions, then it's a bit tricky because I have two time-like directions, right? And it's not, at least not completely clear to me, how to deal with that situation. If I just have those stripes that were, that were between boundaries with normal boundary conditions, then I just really have one time-like. Then I know what to do, right? But if it's really localized in 2 dimensions, it's more complicated. I mean, there are also additional problems, like if you're dealing with, say, these ring-like structures or spots, right? Then your phase dynamics problem is not constant in, quote, time, where time now is the radial coordinate, because as you all know, the Laplacian in R contains these awkward terms, 1 over R and things like this. So it's like a non-autonomous time-like problem. But that problem is not nearly so serious as having 2 time-like directions. So I haven't answered your question, I know. But this not everything is known about this by any means. So people are welcome to join.
Yeah, so again.